So, now that Dr. Professor Landon has returned, we can get started. Today, we're talking about a variety of interesting things. So, to start with, there's actually one little bit in Chapter 3 I should share with you. And so this was proposition 3.6.4, which is kind of yet another weird way of looking at matrix multiplication. So for A in our m by n, m by n, m is in mommy, n is in, and then another matrix. And here we have B in n by d matrix. And n is in nan and p is in Palpatine.
Why would you do the emperor? I don't understand.
Sorry.
I don't understand why you would do the emperor.
Excuse me. Well, you can write AB this way. AB is actually equal to the sum of so-called outer products. So column 1 of A times row 1 of B plus column 2 of A times row 2 of B plus plus column n of A times row n of B. So, you know, how would you prove such a thing? Well, let's look at the AB, the ijth component of this, all right? What's the definition of the ijth component? It's the sum, in this case, k equals 1 to n, of A, I, k, B, k, j, right? Okay, well, what is that? That's the sum, k equals 1 to n, and let's see here. I is free to range up and down from 1 to m. So this is really column, I column of A. How to say this? Yeah. Oh. Sorry. Do something wrong. Let's see, that would be what? That's column, I do think that's the I column of A, right?
Yes.
And the case component of that. And here we have the jth row of B. And that's the case component of the bth row.
I think in your notes you did switch to I and J, so it isn't
What's that again?
I think what you, that's how it was in your notes.
Yeah. So what is this? This is that's wrong with me today. Can't see through that for some reason.
Wouldn't you then just like multiply it out, like column 1 of A, row 1 of B, plus column 2 of A, row 2 of B?
Multiply it out like
I don't know, multiply, but you just like write out what the sum is.
and 30 minutes later we'd still be writing it. But yeah, you could do that.
Well, dot, 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 column n, row n.
Fine.
Just replace.
You drove me to it, Chris. All right, so column 1
What?
of A would be
What?
A1, A11, A1.
No, that's not what I meant. like you do the step that you just erased and then write out the sum from there. And that gets you what you're trying to do.
All right, I'll write out the sum. Let's see here. So AI1, B1J, right? AI2, B2J, plus da 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 da. AIN, BNJ. I mean, I guess you agree with that, right?
Hmm?
I mean, I think we all agree with that. Let me just for a second here, I think part of my stupidity at the moment is I'm not thinking enough about what these look like. So A11, A21, da 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 da, M1, and then eventually we get to A1N, A2N, da 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 da, AMN, right? That's what A looks like. So let's see, as I look at AI1, what am I looking at? That's column 1, right? So this is the I component of column 1 times what?
Row.
Right. The J, yeah, times row what? I guess row 1 of B, right? If the 1 is fixed. I mean, so I guess the point here that I'm just having trouble making the obvious step, which is that this is row 1 of A times row, excuse me, words. Words are hard for me today. Let's try this again. Column 1 of A times row 1 of B, and this is a matrix, and in fact this is the ijth element of that matrix, was the point. Now this is one of those matrix multiplications like we looked at last time, for example, to produce the EIJ. So we looked at this sort of column times row multiplication to give us a matrix last time. And then this continues. Eventually you get to column n of A times row n of B, parentheses ij, but if you add these matrices, if you add these together using the definition of addition for matrices, you get, of course, the claimed column 1 of A, row 1 of B, plus da 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 da, plus column n of A, row n of B, ij. And since this holds for all I and j, that means that the identity is true. Now what I should have done was what I planned to do, which is just talk about the case that B is a vector. Because that's all we really care about for today. Oh well, it's too late. So the corollary to this, which is interesting to us, is take the case B equals to, well, B is an element of just Rn by 1, right? Which we call Rn, right? In that case, and I usually would use lowercase b for that. Well, I usually use x for that, honestly, or b. So I'm setting the big B equal to b. Excuse me. So that means that that's v1, v2, da da da, vn, right? So like row, for example, row I of B, in this case, is just what?
BI.
Yeah, it's just BI, kind of silly. And so this proposition, what it returns for us is A times V is equal to basically your V1, column 1 of A, plus V2, column 2 of A, plus da 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 da, plus Vn, column n of A. And I, you know, over here I have to write the rows on the right-hand side because this is a column row multiplication, which gives you back a matrix, right? But once the rows are just numbers, I can bring them to the other side. It's the same. So this is the way we like to write it usually. So there it is. This is yet another way of looking at the matrix multiplication. let me show you an example of that before I lose you in this sea of indices. So, for example, let's suppose we look at the matrix, I don't know, 1, 2, 3, A, B, C. All right, and I can multiply that by x, y, z. Right? Now, let's see here. Using our dot product, right? We did what we did. Our previous method of calculation was what? We take this, we dot product with the row, first row, right? So that gives me x plus 2y plus 3z, right? And then what did I get? Next I get what?
AX plus BY.
Yeah, ax plus, say, by plus cz. And that has served us well so far, right? But there's another way of looking at this, as is revealed by this so-called outer product identity, the corollary specifically. Here's an example of it in action. So you could rewrite this, right? I'll include an extra step here. ax plus 2y by plus 3z cz, right? You could write this as a sum of these three vectors, right? And then you can factor out the x, the y, and the z. So I've got x times 1a plus y times 2b plus z times 3c. Now, some textbooks on linear algebra will teach this, what I just did, going straight from, you can do an arrow. Some textbooks will actually take this thing I just did, from here to here. They'll take that as the fundamental definition of matrix multiplication. They'll start by defining matrix column multiplication, and then go from there. Some really good books do that. Why is this interesting? You're like, I like the way I'm multiplying these matrices, that's right, I don't need another way.
That has something to do with systems of equations, doesn't it?
Yeah, I mean,
Is that why it's interesting? Or
let's try to put it into a sentence. What is this showing you about the matrix multiplication? This is a what? This is a linear combination. What's that word mean, linear combination? A linear combination of things, what that means is you add things together with weights over whatever field you're looking at. So here, the weights are x, y, and z. So I'm taking a scalar multiple of the first vector plus another scalar multiple of the second vector plus another scalar multiple of the third vector. This is a linear combination of what? Yes, Landon?
Isn't it kind of like terms in the equation? Like, you know how like...
Forget about equations for the moment.
Well, like,
We'll
you
get
know,
back
like
to
the
that.
coefficients in front of each variable, or the, you know what I'm trying to say? They're like terms, and that's the coefficients we call them.
We can talk about an equation, right? But I don't want to talk about an equation right now. What I want to talk about is how do these vectors that I just wrote, these three vectors, how do those relate to the original matrix? Right. It's a linear combination of the columns of the original matrix 1, 2, 3, ABC. That's not something special to this. That's a generic fact about matrix multiplication. That's the takeaway message of this corollary. The product of a matrix times a vector is a linear combination of the columns of that matrix. Okay?
Can you repeat that?
Yeah. So here's an important fact. If we form the product of a matrix times a vector b, what we get is a linear combination of the columns of A. A very specific linear combination, a linear combination where the weights of the linear combination are precisely the components of the vector B by which we're multiplying. It's very simple. But this is a radically different viewpoint than the one we've been taking so far, right? You feel your brain hurting a little bit, that's learning. That's good. You want to feel that. All right, so what? So that brings us to our next important definition for the course, which is called the span. The definition. So let's let S be a subset for us of Rn. All right, so some subset of Rn, then span of S is the set of all, it's a set, okay, of all finite linear combinations of vectors from S. Let me write that out in set builder notation for you, okay? So here it is. Span S. All right, so what is it? What we do is we take a summation, say I equals 1 to k, of Ci, Si, such that what? Such that k is a natural number, obviously. Such that Ci is a real number, and S sub I is an element of S. And of course, these two things are for all I in the numbers from 1 to k.
What is that like?
Yeah, okay, question?
Yeah, does it have to be a proper subset?
No. You could ask what's the span of Rn. So, yeah, that wasn't intentional.
Okay, that's what I was trying to figure out.
Very good, very good. So, we can ask questions like, here's a set of vectors, right? Is another vector in the span of that set of vectors? Let me show you an example. Let's keep it pretty simple. Is E3 an element of the span of E1 plus E2, comma, E1 minus E2? And all of this is happening in R3, okay? There's a question. So, what would it mean for E3 to be in the span? It would mean that we can find an explicit linear combination, right? So let's write that out. That would mean we could write like C1. We're seeking a solution to this equation. C1 times E1 plus E2 plus C2 times E1 minus E2 equals to E3. I mean, if you write these vectors out explicitly, it's immediately obvious that this is impossible. But let me expand on this here. So what we have then is C1 times 1, 1, 0, right, plus C2 times 1 minus 1, 0 is equal to 0, 0, 1. You say, well, we've solved equations before, but not this way. Okay, but the thing Landon was trying to get me to say earlier was what I'm about to say, which is this does correspond to a system of equations, right? It certainly does. What system of equations is that? I mean, you could rewrite this then as a matrix multiplication, and those problems we already own solutions to, right? Like this is what? This is, I mean, a really simple example, but I'm illustrating the general pattern. 1 minus 1, 0. 0, 0, 1, right? That's the augmented coefficient matrix, because this corresponds to 1, 1, 0, 1 minus 1, 0 times the vector of unknowns, C1, C2, equal to the inhomogeneous term, 0, 0, 1. So there's your augmented coefficient matrix for the system of equations we're trying to solve.
There's some solution.
Right, I mean, it's obvious there's no solution. Yes.
And should we be clear, the C's represent constants?
Right. See, because for something to be in the span means there's some set of constants that we can find it. But yeah, obviously no solution. Therefore, E3 is not an element of the span of E1 plus E2, comma E1 minus E2, right? So what is in the span of those two vectors? Well, anything of this form, right? Lots and lots of things. Here, let me show you a different example, which is slightly more interesting. All right, so here's my question. Second example is, and this is another three-dimensional example, here it is 170 an element of the span of, let's say, 1, 2, minus 1, comma, 2, 4, 3, comma, minus 3, 0, 2. So what equation do we have to solve to answer this question, yea or nay? I mean, we have to look for what, like C1 times 1, 2, minus 1, plus C2 times 2, 4, 3, plus C3 times minus 3, 0, 2, which is equal to 170, right? Now remember, this is my sneaky notation, which means 170, right? These are our hidden columns. So if I rewrite this, what do I have? I've got 1, 2, minus 1, 2, 4, 3, oops, minus 3, 0, 2, times C1, C2, C3 equals to 170. I have to solve this system. So when the rubber hits the road, we're back to a row reduction, right? We have to ask, what is the reduced row echelon form of this 1, 2, minus 1, 2, 4, 3, minus 3, 0, 2. I'm reading by columns, and then 170. So you do a calculation, a few steps, and you get the identity matrix. And then in the last column, what you'll find is 83 thirtieths, 11 thirtieths. And finally, 5 sixths. I mean, obviously, right? I mean, everybody can see this. But what I can read from that then is that 83 over 30 times the vector 1, 2, minus 1 plus 11 over 30 times the vector 2, 4, 3 plus 5 sixths times the vector minus 3, 0, 2. Well, guess what? That's equal to 170. So me being tired of writing all three of those vectors at once, I give them a name about S. Let's call this set S, all right? And you can conclude that this is, in fact, yes, an element, not an element, listen, good gracious, an element of the span of S. Yep.
So basically, you're seeing if it's equal, if you can do the reduction, whatever.
Or are we checking, like, to see, like, are we later gonna just add them all up to make sure that it actually makes equal something like this?
Yep. You will see if it's possible, and you will add them up, yes? I will ask you both questions. Is it in the span? And if so, how is it in the span? The fact that it's in the span is answered by this. At this point, I can already see, yeah, it's in the span. I can choose C1 equal to that, C2 equal to that, C3 equal to that. This is here I'm explicitly showing you the linear combination of vectors which produces the vector which is in question, whether or not it's in the span. If you're asking me what the answer is, you're kind of asking the wrong question. The real question is, what's the concept? I want you to understand it from many different angles. So if you're asking me what the agreed upon answer is to this kind of question, I don't have an answer for that. I want you to understand the concept. I hope that concept is starting to become clear. What should be clear by now is that we don't really need to make this step, right? Like, once you understand this, you see that there's a theorem to state here about whether a vector is in the span of a given set or not, right? I think we can state that theorem at this point, right? Let me state the theorem for you. Once we have this theorem, now that we've seen these examples, we can understand that we don't need to do quite so much writing for given explicit examples, right? So here's the theorem. If S is, and I need the S to actually be finite for this to make sense. So suppose S is equal to S1, S2, and so forth. You got K of these guys, right? Then D is an element of the span of S, only if the reduced row echelon form of the matrix S1, S2, Sk, B, corresponds what? To a consistent system of equations. Moreover, we can read the explicit linear combination of the S1 Sk, which attains B from star. That's what we just did in both of these last examples. And there's nothing stopping us from doing it in general. I'll give you guys a second to write that down. I can't show you some more examples. Everybody get it? Yes, Chris?
What does that say when it says linear combo of something?
S1 through Sk. These vectors. All right, I have a couple more examples. I'm going to show you on the projector because, as you see, it takes a long time to write out an example, but there's not really much. I mean, what makes the example hard? What would actually take you time in this calculation? Yeah, the same thing as usual, the Gaussian elimination, right? Or the rref. What's that? Yes, there is technology to do it. However, that technology is not available to you on the first exam, so while I don't discourage the use of technology, I would remind you that you need to get strong enough that you can do it. Because it's generically true that given enough time, anybody can do my first exam. The question is, will you have enough time? Okay, I mean, calculating the reduced echelon form is a fun game, right, basically? You like playing games?
I have a question along these lines. Are we allowed to use a calculator on the first echelon?
No,
Okay,
I mean, a little one, yes.
okay.
Graphing, no. I mean, sorry, eventually I will reach chapter 4. Here we are. Okay, guys. You know, sometimes on the exam, I will actually give you the row reduction and then ask you to interpret it too. So it doesn't, I mean, it won't be the case that absolutely everything on the test you have to calculate, right? Sometimes I just like to test your ability to interpret results. So, you know, there's more than just calculating, there's thinking. I mean, Gaussian elimination does require thinking, right? But it's kind of a boring sort of thinking, you know? Okay, anyway, it's not about the stupid test, I'm afraid about that anyway.
People who want to pass.
Oh, people who want to pass? Yeah, passing is optional. Let's see here, so.
It is, but at the same time, it's important.
So here's a question. Yet another three-dimensional, I seem to be stuck on a theme. 2 vectors in 3 dimensions, or 3 vectors in 3 dimensions, and a third vector. Anyway, here it is. I've got this v, this w, and there's the vector v. The question is, basically, can I solve this equation? Now, you guys should recognize that if the spanning question is v in the span of v and w, right? And here I'm using x and y instead of c1 and c2, but I hope you can see conceptually it's the same animal. Okay, so I try to solve this equation, which means I try to solve that equation, which means I really try to solve this equation. Bam. So the answer is yes, it is. Because if you take 1 copy of v plus 2 copies of w, you get v. And you can see that. If I take 1 of these plus 2 of these, I get 2 plus 2 is 4, minus 1 plus 2 is 1, 3 plus 2 is 5. Works. Hey, does that mean if I can just see by looking at the 2 vectors how one is a linear combination, well, the third one's a linear combination of the given 2, that means I've answered the question without all this calculation?
No.
No, it does. It actually does mean that. We forget this sometimes, but guessing is a legitimate solution. The question is it an attainable solution? I mean, honestly, folks, the most clever solution is the simplest one. The most clever thing you can know on a test is the answers, to write them down. The question is whether or not we as instructors permit you this freedom.
The question is, will you?
Or whether or not we take advantage of the freedom.
I mean, some of us have a dim view of students. We think, the student must have cheated. But on my spanning questions, there's some chance you could just look at it and go, he added the first 2 to get the third. You know, I mean, it might be that. Geometrically, it's interesting to ask what that question means, that last thing meant. You can view it as basically meaning that all 3 of those vectors lie in the same plane in 3 dimensions. So like I can take the v plus the 2w and get the 4, 1, 5. In other words, I can take the v plus 2 of the w's and I get to here. So I mean, there's a geometric meaning to it, which we'll talk more about later in the course. But I try to focus on the algebra here because, you know, geometry helps some people, but it hurts others, and I don't want to breed uncertainty. You don't really need to understand much of anything geometrically to be totally successful at the first test. I don't really test much on geometry yet, okay?
Yes.
I test algebra. What's that?
You said yes.
Yet, oh yes. Here's another one. Is E3 in the span of B1, B2, B3? Where B1, B2, and B3 are these guys. So again, I think by now you're starting to get the idea. That plus the third, plus the second one, plus the third one equals E3. You try to solve this system of 3 equations. Yeah.
So if you're asking if it's in the span, does that mean that it has to be like the solution or a possible solution?
The span is defined. The span is defined to be all possible linear combinations, finite linear combinations of the given set of vectors. So it always boils back to what is a linear combination? It's adding vectors together, right, with coefficients which are not known. And yeah, those unknowns correspond to unknowns in a system of equations. So yes, the question of spanning always comes back to a question of solving a system of equations. at least to start with. We do later find theorems which allow us to get around direct calculation, sometimes. In this case, you do the row reduction, and out pops this guy. And that shows you that if you take 0 copies of B1, oh, this is wrong, that should be gone. Hey, Landon, you missed one.
Well,
You're not here yet, are you?
no, I'm trying to still understand.
No, okay, that's cool. Landon has found other errors, like I should keep some sort of blog of the errors he
Did you
brings
see
to
the
me, so
one
you
where
guys
you had the,
What's that?
did you see the one where you had the unit vector, E1 as 0, 0, 0, instead of like 1, 0, 0?
Maybe. I'm not.
It's right in your inverse matrix calculation thing. It's pretty confusing. I mean, people can work around it, but it's
Well, why don't you guys email me when you find something like that?
because it's funny to just mess around with it. No, I'm kidding. It's because I have been busy doing your homework.
No.
I haven't had the time to email you.
I know, it's like such a time-involved thing to email me, but like, I don't care. You don't even have to put Dear Professor Cook or Dear Exalted Leader, Dear
Dear son.
You can just write the question. I don't care. I am not stuck on whatever.
Also, the
So
sentence.
that shouldn't be there. It should just be 1/2 B2 minus 1/2 B3, right?
Since it works.
Since they took. Okay, so moving along here, guys. Was there a question? I mean, these are more of the same. Here I have 1, 2, 3 vectors is W in the span of those 3 vectors. It's the same thing again and again. I mean, we stop. I think I've shown you enough. All right. Here's a more interesting question. What if you have 2 vectors and you want to ask, are 2 vectors in the span at the same time? How would you answer that question? How would you answer 2 spanning questions at once?
The same way, just read off differently.
Right? So here's an example actually of this. So each spanning question is a system of equations, right? But it's a system of equations with the same coefficient matrix. Right? You fix the spanning set S, and then is B1 in span of S? Is B2 in span of S? Is B3 in span of S? Okay, well that's 3 systems of equations, each with the same coefficient matrix. That means we can use the trick we used in solving for inverses again. We can solve all of those systems at the same time because they share the same coefficient matrix. So here's an example. Let W be the span of E1 plus E2, E2 plus E3, E1 minus E3. Then I ask the question, here's a T, E1, E2, E3 minus E1. Which of the vectors in T is in the span of S? I don't have to do 3 separate calculations. I can do one big calculation and answer all 3 of those questions at once. Here's how it goes. So what I do is I just take, here's the vectors in S, here's our candidates for the span of T, right? Candidates for the span of S. These are the vectors from T, which might be in the span of S, might not, we don't know. Let's find out. Row reduce, get down here, bam. Get this row of zeros. 1 and minus 1. Aha! That tells me then that these 2 guys, the ones these 2 guys, are not in the span of S. So E1 and E2, not in the span of S. I can see that from this calculation. Like, on the other hand, if you look at this one, see, 0, 0, 0. I've got minus 1, 1. Hey, you know what that tells me? That tells me yes. E3 minus E1, in fact, is in the span of S. And let's see here, I can see what it is. It's, well, you got choices, right? Let me turn the lights back on and talk about E3 here. Thanks. So let's see here, what do we see about E3? I'll write it over here. So if you'll allow me to use, so we're basically asking the question C1 times what, E1 plus E1. E1 plus E1, Landon. Right here. Yeah, that's a 2. E1 plus E2. I'm sorry, I
I'm sorry.
I have not been giving you proper respect today. Dr. Professor Landon,
Oh, thank you.
I will remember that. Okay, so E2 plus E3. C3. Oh, yeah. E1 minus E3, right?
Yeah.
Now, as soon as I write this down and I ask, does this have a question? Does a solution jump out at you? Jumps out at me. Forget all this matrix garbage. Just look at this.
Yeah.
0, 0, minus 1. This is just minus that vector. So of course it's in the span. This is just a scalar multiple of one of the vectors we're asking about. So scalar multiples of vectors building the span are in the span. Another fun fact, the vectors in the span are in the span. Just take a really, what's a really stupid linear combination? 1 times vector plus 0 times the rest. It's a linear combination. But okay, let me stop. But getting back to the row reduction, what we actually see there, right, is that C1 plus what? C1 plus C3 is equal to minus 1. And what's the other? C2 plus what? Well, C2 minus C3, right? C2 minus C3 is equal to what? 1. So generically speaking, what do we have? We can use C3 as a parameter. We've got C1 is equal to minus 1 minus C3, and we've got C2 is equal to C3. And of course we've got C3 is equal to C3. I mean, that's, okay, fascinating. So what that means is I could take minus 1, I'll use a t rather than C3 just for a second here. Minus 1 minus t times E1 plus E2 plus t times E2 plus E3 plus t times E1 minus E3, right? Did I do something wrong?
Isn't it supposed to be C2 equals 1 plus C3?
Oh, yeah. Sorry. I knew something felt wrong here. Where would that have affected
In
me?
the regular T.
And is my C3 right? Yeah, C3 is, well, yeah, C3. Yes, what else did you want?
Well, I'm just confused as to where you got C1 plus C3 equals -1.
Top one.
Oh, from here. So this equation is C1 plus C3 minus 1.
What about the other one?
Yeah, what about the other one?
Column 2.
I'm not looking at that. I'm asking about the coefficient matrix and this last column. I'm ignoring these two at the moment. I already know those are inconsistent. Those aren't in the span.
Because they aren't the same thing as the other side?
Because this is a row of zeros with a 1 here, that means there's no solution. There's no way to get this vector E1 or that vector E2 in the span of S here. And that's why I think that's why this example is partly interesting, is because you have both phenomena. You have some vectors in the span, you have some vectors outside the span, right? Just the third one's in the span. It's kind of stupid how it's in the span, but I won't. Oh, there it is. And so all of this will be equal to E3 minus E1. And if I did my math right, that's for all t in the reals. So it's not just one way of finding it in the span, there are infinitely many ways of finding it in the span in this case. I think the one we just get, I mean this, we saw this equals to that, right? That would correspond to setting t equal to what? -1, right? In my general solution down here. So like t equals -1 makes this go to 0. And it makes this go to 0, right? So t equals -1 kills this term and that term, and just leaves me -1 times E1 minus 3 equals E3 minus E1. That's actually an important comment to make because it may not be a unique situation. You may be able to find a vector in the span in many, many different ways. Corresponding to the fact when we look at equations, we can have infinite solutions, right? There can be many, many different ways to find a vector in the span. which in some sense is kind of annoying, right? Like, partly you want to look at problems where you just have one way of finding vectors in the span, am I right? So that brings us to our next topic, which is linear independence. All right, so these things I showed you today, these are your basic tools for solving spanning questions. I don't really have much more to say to you. After you work about 4 or 5 of these, you should get it, and it should become boring to you, I hope. Maybe it's already boring to you, but for the right reasons.
Not the most boring, just be boring. Like there's 2 kinds of boring. There's the boring because you don't know how to do it, and then there's boring because you know how to do it because you've done it so many times.
Yes, I want the latter.
Yeah.
Before. So,
How would you do that?
what's the definition of linear independence? Well, I'll tell you what, I'll tell you that next time. Let me just talk to you about what linear independence is this time. Probably spelled it wrong. Is it with an A or an E? I can't remember.
R-N-D-E.
Oh,
R-N-D-E.
sometimes I want to make that an A.
Or some.
You never dance alone. That's why it's independence instead of independence.
Oh, it's called independent.
Seriously, you never dance alone. That's why it's independence instead of independence.
But what does the E contribute?
You could dance alone if you wanted to. Like, what if you don't have anyone to dance
You
with?
have no rhythm.
Dance like
It's the same reason why you want more deserts, or do you want more desserts? And dessert is called
That's
D-E-S-S-E-R-T,
where we're coming to.
and desert is called D-E-S-E-R-T. Whatever, anyway.
Okay, so let me just show you some examples.
This is all on
The more you know.
Oh my gosh. I was curious, man. This was not reduced.
Just some examples, all right. A set of vectors is said to be linearly independent if there's no way of taking one of the vectors in that set and forming it as a linear combination of the other vectors in the set. So in other words, a linearly independent set is a set which has no non-trivial linear dependences. I mean, there's always a trivial linear dependence in any set, right? You take the vector, for example, and I write 1, 2, 3 as a linear combination of 1, 2, 3? In fact, I can. It's 1 times 1, 2, 3. There you go. There's a linear combination. In the stupidest sense of the term, that's a linear combination. It's a scalar multiple. One thing added to itself. That's it. So that is not interesting, right? So ignoring those kind of stupid linear dependences, the question is, are there interesting linear dependences in the set? And there are. In this first one, what is it? So this one I could say 2 times 1, 2, 3 minus 2, 4, 6 equals to what? Yeah, equals to 0. So there's a non-trivial linear dependence between the vectors. Now, pragmatically speaking, the second one is a scalar multiple of the first, right? There is something you can take away. Anytime you have one vector being a scalar multiple of another in that set, it's not going to be a linearly independent set. This guy is linearly dependent because the third vector, dependent, okay? The third vector is a sum of the first two. So there's an obvious linear dependence here. I mean, you can take b plus w minus b plus w. There you go, that's equal to 0. In other words, I've got c1 equals to 1, c2 equals to 1, c3 equals to minus 1 in the language you've been using today. There's a non-trivial linear dependence which gives you back 0. That proves that that's a linearly dependent set. This guy, on the other hand, finally is an example of a set which is linearly independent. If I take, there's no way I can write one of these basis vectors, right, one of these standard basis vectors as a linear combination of the other ones. In particular, if you look at C1E1 plus C2E2, look at the dot CNEN, and you set it equal to the 0 vector, which would be what, 0, 0, dot, 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 0. If you rewrite this as a vector, you got C1, C2, dot, 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 Cn equals to 0, 0, dot, 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 0. What does that say about C1 through Cn?
For all 0?
Right, they're all 0, because in order for an n-tuple to be equal to another n-tuple, it must be the case that each and every matching slot matches. So, yes, in fact, C1 equals C2 equals dot, 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 equals Cn equals to 0. So, usually, more often than not, what I take for the definition of linear independence is what we discover in this third example. The definition of linear independence is this, as I'll write out carefully next time. If you take an arbitrary linear combination of the vectors and set it equal to 0, it must be that that linear combination was nothing more than the trivial combination. In other words, all of the coefficients were 0. So next time, we will talk about that, and we will discover this wonderful tool called column correspondence property, which will help us to ascertain the linear independence of sets of vectors in Rm with blazing efficiency.
Does anyone want to do like a study tomorrow?